Hello and welcome to this video. Starting from this video, we are going to study complex numbers, and complex numbers are a very important topic when you are preparing for a competitive exam or for your board exams, because complex numbers has got lots of theory involved with it. So a lot of different kind of problems can be formed related to the concepts of complex numbers. So let's get started. So as I have written here, complex number is a combination of real number and imaginary number. So we all know what is a real number. Now, the new thing which we have here is an imaginary number. So what is an imaginary number? Square root of any negative number is an imaginary number. Since the square root of a negative number does not exist, these are called imaginary numbers. And these numbers cannot be used for counting. Now, the application of complex numbers applies a lot when you will progress in your mathematical studies. Advanced courses like complex analysis or system of equations, when you deal with something like Riemann hypothesis or Dilbert 10 problems, complex numbers is quite involved in those kind of theories. Now, a real number, for example, 1, which is given here, can be treated as a complex number with having imaginary part as 0. The symbol for square root of -1 is called iota, which is shown here. We will typically use I or j to denote this. Now you can clearly see that I square will be equal to -1, I cube will be equal to -I. I square will be -1 because you take out the square root here, so it becomes -1. I cube will be I square into I, so it becomes -I. I to the power 4 will be 1 because I to the power 4 is I square square, so -1 square is 1, and I5 would be I to the power 4 into I, so it becomes I, and so on. Now if you see carefully, then if you multiply I to the power 4 with I square, I cube, and I to the power 4, that is 4 powers of I, then the results will repeat. As you can see here, I to the power 5 is I to the power 6 is -1, I to the power 7 is -I. So it keeps rotating among 4 values. That is, I to the power 4m will be 1, 4m plus 1 will be I, 4m plus 2 will be -1, and 4m plus 3 would be -I, where m is in the set of p. Here p represents positive integers, including 0. Now there is a note here. So we can write 1 is equal to square root of 1, and this one we can write as -1 into -1, which is equal to I into I, which is equal to -1. Now this is not correct. The reason is this step. You cannot write square root of 1 is equal to square root of -1 into -1, because the power of minus over here is half, and this power is also half. So when you will take out the square root, it will be equal to -1. So this step is misbehaving. You cannot have this. A complex number we typically write as a plus ib or x plus iy, where ab and xy, that is are all real numbers. And the number itself we typically denote by z. Here x or a will be called real part, and b or y will be called imaginary part. So real part is also written like rez, and y is also written like imz, re for real and im for imaginary. Now if the imaginary part, that is y or b, is 0, then the complex number is purely real. And if a or x are 0 and b and y are not 0, then the complex number is purely imaginary. Now you can clearly imagine that when you think of 0, 0 can be written as having real part 0 and imaginary part 0. The set of all complex numbers we typically denote by C. Now, two complex numbers Z1 and Z2 are said to be uh, equal. This shouldn't be true. This should be equal if their real parts, their spelling is wrong. Real parts and imaginary parts are equal. That is, Z1 is equal to X1 plus IY1 and Z2 is equal to X2 plus IY2. Then for Z1 to be equal to Z2, X1 should be equal to X2 and Y1 should be equal to Y2. Now we will perform simple operations. Addition is simple. You combine real part with real part and imaginary part with imaginary part. So A plus IB plus C plus ID becomes A plus C plus I into B plus D. Subtraction is also simple. You subtract real part with real part and imaginary part with imaginary part. So A plus IB minus C plus ID becomes A minus C plus I into B minus D. Multiplication is simple, but for the first time I'll explain. So suppose we have A plus IB into C plus ID, then we get AC plus IBC plus IAD plus BDI square. Now I square is -1, so it will become real, and the result will be AC minus BD plus I into BC plus AD. For division, we need to rationalize. That is, we want to make the denominator a pure real number. So we multiply this with this C minus ID and also divide with C minus ID. So you get the final value as AC plus BD plus I into BC plus AD divided by C square plus D square. Now there is something called conjugate of a complex number. So suppose Z is equal to X plus IY is a complex number, then the conjugate of this is written as Z to the power bar, overline, or bar is written over Z, and that is equal to X minus IY. So this is called conjugate or complex conjugate of the complex number Z. Now we have certain properties of conjugates. Z1 is equal to Z2 implies that conjugate of Z1 is equal to conjugate of Z2. That is, if it is X1 plus IY1 and it is X2 plus IY2, then X1 is equal to X2 and Y1 is equal to Y2. Here, this will become X1 minus IY1 and this will be X2 minus IY2. So you can see that X1 will be equal to X2 and Y1 will be equal to Y2. So it is both ways it will be satisfied. Similarly, it is conjugate of Z, and then you again take conjugate. This bar is not a proper place. That will be equal to Z. So suppose Z is equal to X plus IY, then conjugate of Z is equal to X minus IY, and then conjugate of Z is X minus into minus IY, which is X plus IY, which is equal to Z. Now Z plus conjugate of Z is equal to 2 twice real of X. So you see that X plus IY plus X minus IY is equal to 2X, which is equal to twice of real of Z. This should be Z, not X. And over here, this should also be Z. So similarly, we can say that Z minus Z bar is equal to 2Y imaginary of Z. This should be Z. So we similarly substitute the values, we get 2IY, which is equal to 2Y imaginary of Z. Now, if Z plus Z bar is equal to 0, then Z is purely imaginary. So we add this, we get 2X, which means if this is 0, then this should be real. If it is 0, then it is purely imaginary. If Z is equal to Z bar, then Z is purely real. So if X plus IY is equal to X minus IY, then 2IY becomes 0 because X will get cancelled. This goes to left hand side, so 2IY is equal to 0. And so Z is purely real. Next property is Z bar is equal to X square plus Y square. So we multiply here simply and we get X square plus Y square. Another property would be, I will get confused in this. Okay. Conjugate of Z1 plus Z2 is equal to conjugate of Z1 plus conjugate of Z2. This should be Z2. So there are lots of typing mistakes. So we take the conjugate of this big number x1 plus iy1 plus x2 plus iy2, which is equal to x1 plus x2 plus iy1 plus y2. And then we remove the bar and we make the imaginary part negative, which is same as conjugate of z1 plus conjugate of z2. Now, ninth property is conjugate of z1 minus z2 is equal to conjugate of z1 minus conjugate of z2, which you can prove like 8. 10th property is conjugate of z1 z2 bar is equal to, now this is wrong. This should be conjugate of z1 into conjugate of z2, so which you can prove like 8. Property 11 is conjugate of z1 by z2 is equal to conjugate of z1 by conjugate of z2 if z2 is not equal to 0. This also you can rationalize and prove it, so I have left it as an exercise. Property 12 says that if p of z is equal to a0 plus a1z plus a2z square plus up to an zn, where this is a0 not s0, a0 up to an and z are complex numbers, then conjugate of pz is equal to conjugate of a0 plus conjugate of a1z plus conjugate of a2 conjugate of z square up to conjugate of an and conjugate of z to the power n is equal to conjugate of p, which is a function of conjugate of z, where conjugate of p of z is equal to conjugate of a0 plus conjugate of a1z plus conjugate of a2z square plus conjugate of n into z to the power n. So this also you can prove easily, and I have left this as an exercise. Property 13 is if r of z is equal to p of z by q of z, where p of z and q of z are polynomials in z and qz is not equal to 0, then conjugate of r of z is equal to conjugate of p of conjugate of z is equal to conjugate of q of conjugate of z. So this also you can prove yourself. We'll use these properties when we solve the problems. Now, if z is equal to a1, a2, a3, b1, b2, b3, c1, c2, c3, then conjugate of z is equal to conjugate of a1, conjugate of a2, h3 bar, I'll simply say h3 bar, b1 bar, b2 bar, b3 bar, c1 bar, c2 bar, c3 bar, where ai, bi, ci are complex number and value of I is equal to 1 or 2 or 3. Now we will study modulus of complex numbers. So if there is a complex number z, which is denoted by z between bars and is equal to the real number square root of x square plus y square. So you can see here r is missing and then extra t is here. Lots of typing mistakes are there. So now we can observe some properties of modulus. So modulus of z is equal to 0. If modulus of z is equal to 0, then z is equal to 0. So x square plus y square is equal to 0, which will imply x is equal to 0 and y is equal to 0. Because square of real numbers cannot be equal to 0. So if the right hand side is 0, then the individual terms have to be 0, for which will imply z is equal to 0. Mod of z is equal to mod of z bar. So now this is also equal to minus mod of minus z and mod of minus z bar. And all these four are equal to x square plus y square. So it does not matter whether the number is x plus iy or x minus iy or minus x plus iy or minus x minus iy. So all four numbers will be x square plus y square. Property 3 says that minus modulus of z is less than equal to real part of, this should be again z, this x should be z. So minus z real part of z less than equal to modulus z. So you can see that minus of x square plus y square is less than equal to x square less than equal to x square plus y square. Now you will say that how I have written x square or this or this. So what I have actually done is I have squared everything, in the sense that modulus of z is x square plus y square, square root of x square plus y square. So I have squared that value and I have written x square plus y square. I have squared this and I have written x square, and I have squared this, which is x square plus y square. And similarly, property 4 is also there. Property 5 says that z bar is equal to modulus z whole square. So if you multiply x plus iy with x minus iy, you will get x square plus y square, which is equal to mod of z square. Property 6 says that mod of z1 z2 is equal to mod of z1 multiplied with mod of z2. So you substitute the value of x1 z1 and z2 here. So you get x1 x2 minus y1 y2 plus I x1 y2 plus x2 y1. Then the mod of this would be square root of x1 x2 minus y1 y2 whole square plus x1 y2 plus x2 y1 whole square. Now if you see this will have a term 2x1 x2 y1 y2, and this will have a term 2x1 x2 y1 y2. Both will be opposite in sign, which will get cancelled. So what will remain here is x1 square x2 square plus y1 square y2 square, and here we will have x1 square y2 square plus x2 square y1 square. Now these four terms will be equal to x1 square plus y1 square into x2 square plus y2 square, which is nothing but modulus of z1 into modulus of z2. Property 13 says that modulus of z1 by z2 is equal to modulus of z1 by z2 if z2 is not equal to 0. So you can study all this, and I'm not going to just read it out. You can study and try to prove this yourself. If you get into a problem, let me know in comments and I will move forward. So now we are going to study more about complex number. So a complex number that we have, which is x plus iy, it can be represented by a point P in the sense of, the xy plane. So in this case, this is complex plane. That is, y will represent the imaginary axis and x will be the real axis. So this plane is called Argand plane or complex plane or custom plane. Now point P is also called the image of the complex number, and Z is also called the affix or complex coordinate of point P. Modulus will be given by the length of the segment OP, which will be equal to square root of x square plus y square, which is nothing but mod of Z. This is repeated information. Z is length of OP. So if we see the complex plane, this is our x-axis, which will represent the real part. This is y-axis, which will represent the imaginary part, and this is point P, which is x plus iy. So OP, that is this length, is nothing but modulus of z, and argument of z is theta, that is the angle this will make with positive direction of x-axis. By positive direction, we mean that it is counterclockwise. So theta is argument of complex number. Then we can see that suppose we rotate it with one full circle and then again with theta, that becomes 2 pi plus theta. We rotate again, it becomes 4 pi plus theta. So it will be actually 2n pi plus theta, where n will be a set of integers. You can rotate in other direction also, so it can be negative as well. That is why it is set of integers, not set of positive integers. Now always the principal argument will lie in either pi or minus pi. That is called principal argument. So when you add 2 pi to that or subtract 2 pi to that, then it does not remain principal argument. Now clearly arg of z will be tan inverse y by x. That is this by this. Tan theta is equal to y by x when P is in the first quadrant. When P will be or Z will be in second, third, and fourth quadrants, then in case of second quadrant, it will be pi minus tan inverse y by mod of x, because if it is in this, then x becomes negative. So you can make x positive and then subtract that from pi. If it is in the third quadrant, then it is minus pi plus tan inverse mod of y by divided by mod of x. So this means that this is in the third quadrant, that is over here. So you take minus pi and then you take tan inverse of that and then add that. And similarly in fourth quadrant, it is equal to minus tan inverse mod of y by x. Now it also has a polar form where we write that z is equal to r cos theta plus I sin theta. In this case, r will be equal to mod of z and theta is equal to argument of z. So if you consider the rotations also, the general form is given by r into cos of 2n pi plus theta plus I sine 2n pi plus theta, where n is the set of integers. Now, Euler gave a formula for this complex number, which is denoted by e to the power I theta. In this case, the value of r is 1 over here. So, the general equation will become r e to the power I into 2n pi plus theta, where r will be the modulus and then cos 2n pi plus theta and I sine 2n pi plus theta will be represented by e to the power I 2n pi plus theta. Now we will study some properties of arguments. Now, as I said in the beginning, complex numbers has got lots of theories, so there will be some videos, more videos will be involved in this. Now we consider that Z, Z1 as Z2 as three different complex numbers, then argument of Z bar is equal to minus for argument Z. You can clearly see that if Z is equal to xy and Z bar is equal to x minus iy, so this is easily satisfied. Now argument of Z1, Z2 is equal to argument of Z1 plus argument of Z2 plus 2k pi, where k will be 0 if sum of arguments lie between minus pi and pi. K will be 1 if the sum lies between minus 2 pi and minus pi. And k will be 1 if the sum of arguments lie between minus pi and 2 pi. So this you can easily verify. I mean, you can verify all the results because I'm not going to prove a lot of these. Argument of Z1, Z2 bar is equal to argument of Z1 minus argument of Z2. So you can see from here that argument of Z bar is equal to minus argument of Z. So you can think of this like negative that. Now argument of Z1 by Z2 is equal to argument of Z1 plus argument of Z2 plus 2k pi, where k is same as item 2, that is this item, and the plus sign between Z1 and Z2 is replaced with negative sign, that is these will be replaced with negative sign. Z1 plus Z2 mod okay. So if mod of Z1 plus Z2 is equal to mod of Z1 minus Z2, then argument of Z1 minus argument of Z2 is equal to pi by 2. So how you can understand this is, suppose this is our argand plane, there is a Z1, there is a Z2. So when you add this, you will get another Z2, another Z, right? So in this case, what will be the real part? It will be x1 plus x2 and the imaginary part will be y1 plus y2. So if you take the mod, then it will be x1 plus x2 whole square, and then other part will be y1 plus y2 whole square, and you take square root of all that. And this mod will be also the same. So if they are both are equal, then argument difference will be pi by 2. To understand this mode, you will have to wait when I deal with the geometrical representation, then you can clearly see how this is going to work out. Property 6 says that Z1 plus Z2, modulus of Z1 plus Z2 is equal to mod of Z1 plus mod of Z2 implies argument of Z1 is equal to argument of Z2. Square of mod of Z1 plus Z2 is equal to R1 square plus R2 square plus 2R1 R2 cos theta 1 minus theta 2. Square of Z1 minus Z2 modulus is equal to R1 square plus R2 square plus 2R1 R2 cos theta 1 plus cos theta 2 plus theta 2. So all this you can verify from the given formulas. Now we go and we look at vector representation of complex numbers. Now by vector representation, what we mean is length is the modulus and the argument is the theta angle which it makes with the real axis. Now this is denoted as OP with the right arrow, and this OP represents the vector of the complex number Z. So with this, I will come to the end of this video, and in further videos, we will deal more about with the vector representation of complex numbers and more properties involved. So as we proceed further, these points will become clearer because I have not explained everything in this video. Yes, I'm taking a shortcut here. the proof is left for you. So you should go and work out on these properties and try to prove them by yourself. If you have question about any of these properties, you can let me know in the comment and I will explain it. And the slide will be available on GitHub, which will be given in the description. So if you have found this video useful, please subscribe to the channel and like the video so that it can reach to more people, because that's how YouTube algorithm works. I'll see you in the next video where we will deal with vector algebra of complex numbers. Thanks a lot for watching. Enjoy.